Well, next I'm going to talk about another form of induction, which the book calls the second principle of mathematical induction. I'm used to seeing it called strong induction. It's just a minor difference. It goes like this. For a natural number greater than 1, if all of the statements from that natural number m, from P1 to Pm, if all of them are true, and for k at least m, if all of the statements from 1 to k implies that pk plus 1 is true, if all of these true implies pk plus 1 is true, then Pn is true for all natural numbers n. So in the induction hypothesis step, we're not simply assuming that the kth statement is true to prove k plus 1. We're assuming that statement 1 all the way up to k are true to prove k plus 1. And I'm not going to do an example, so let me state a theorem that could be proven easily with this strong induction and not so with regular principle of mathematical induction. There's a unique factorization theorem that says every natural number greater than 1, so from 2 on, can be broken down into a product of its prime numbers. Well, just think about it this way. Suppose I need to prove that the number 21 can be factored into a product of prime numbers. Does knowing that the number 20 can be broken down into the product of prime numbers help me at all? It doesn't, because 20 doesn't go evenly into 21. But if I assume that all of the numbers from 2 up to 20 can be each broken down into product of prime numbers, now when I get to 21, I don't have to look back just at 20, but I know 7 and 3 can both be broken into the product of prime numbers, and 21 happens to be 7 times 3. So I'll take the unique factorization for 3 and for 7. Why did I pick those examples where 3 and 7 are both prime numbers? I don't know, but it still holds true. So that would be an example of where you need to use the strong induction, or the second principle of mathematical induction. And this short theorem here says something that I mentioned earlier. For either the principle of mathematical induction or the second, the strong induction, the base case might not be n equals 1. In fact, it doesn't even have to be a positive number. N is actually a variable, so it could be that there are negative numbers. The base case could be any integer at all.